Hi, everyone. Welcome to today's Applied Math seminar. Our speaker today is Frank E. Curtis. He's a professor at the Department of Industrial Engineering at Lehigh. He holds a PhD from Northwestern, and before he came to Lehigh, he did a 2-year postdoc stint at Court Institute in New York. He received various highly prestigious prizes, including the Lagrange Prize in Optimization and the Informs Computing Society Prize. His research focuses mostly on large-scale nonlinear optimization, and today I think he's going to talk about some stochastic twists. And so without further ado, there we go.
Okay, great. Well, thanks everybody for coming. Thanks for the invitation. It's great to be here, if only virtually. I'd like to talk today about some of the recent work that I'm doing with my group. It's on a collection of papers, and actually we have a few ideas for where to go from here. And so we're excited to talk about sort of the path that we're planning to do. I will like to just thank all of my co-authors, obviously, and hopefully we find this interesting. When I've given this talk a few times already, it's little short in the sense that it probably doesn't fill up a full hour, but maybe that will leave some time for questions and discussion at the end if everybody wants. So here we go. I'm gonna click again here. So the collaborators that I was working on this here is Albert Barajas on the left. This is he's at the University of Michigan now. He was a postdoc at Lehigh. There's Daniel Robinson, who's also a professor here at Lehigh. Baoyu Zhou, who's a student of mine who's graduating this year from Lehigh, and then Michael O'Neill, who is a postdoc at Lehigh now, and before that was in Wisconsin. Just checking. I don't know if I had the chat open or not, but so most of this talk is going to be about a paper that has already appeared in the Science Journal of Optimization. That's the first one mentioned here. Sequential quadratic optimization, and so on. The other papers are on archive, or they've been submitted, and the last one is a working paper. Basically, there's, as I'm going to try to explain, we can think of tons of extensions of the initial paper that we submitted, and I actually, I highly encourage if others who find this work kind of interesting and applications to pick this up, and it'd be great to hear of possible ideas people have. I'm going to try to give you a motivation. And basically what I'm going to do in this talk is marry two types of algorithms that you may have heard of in the continuous optimization world. On the one hand, we have the stochastic gradient method, which is sort of well known now, especially in use in machine learning, signal processing, and so forth. Describe a little bit of that in terms of the algorithm, in terms of what we need in terms of the analysis for that. What we're going to end up doing, though, is we're going to end up merging that with another strategy or methodology for constrained optimization that's been around. That's SQP, sequential quadratic optimization, or sequential quadratic programming for solving constrained problems. And I would say putting these two things together is sort of non-trivial, but we're going to explain how we do that exactly and why this leads to some interesting opportunities for doing some analysis, but also hopefully algorithms that work well in practice as well. At least they seem to from what we've done so far. So just to motivate the work a little bit, though, I'll just say, okay, we have constrained optimization more generally. So sort of classical type of general problem statement here, where we have an objective function with some explicit constraints defined by functions CE and CI. We're going to assume that we're in the continuous world. The functions are all smooth. All right. So obviously you can go in different extensions from there, but that's where going to be our starting point. Tons of applications people have looked at these kinds of problems, sort of like where physical constrained problems, and PDE constraint optimization, or operations research type problems where you have resources trying to minimize costs subject to resource constraints, so on and so forth. Plenty of a long history of algorithms of different types, penalty methods, SQP, interior point. All of these algorithms, generally, you find papers in the literature that talk about, or even textbooks about talking about some comprehensive convergence theory, that often relate to, making different assumptions about constraint qualifications, which I'm going to touch on a little bit, which is why I mentioned it here. And there's effective software. So there's IP-opt is well known, Nitro is well known, Loco, and so many others. I wouldn't say that this is a solved problem. There's still, work to do in this area, but in the deterministic world with constraints, everything is smooth. There's a lot that's been out there already. What has also been out there, but is maybe a little bit sort of still clearly many things to do, is the setting of having stochastic constraints. So imagine you have an objective function, again, that's smooth. So maybe equality constraints again. Maybe they might also be stochastic as well, but I'm just writing in here of maybe inequality constraints that are they're defined by some involving some random variables. And so with this kind of stochastic constraints and maybe probabilistic constraints, the way you think about it, there's different paradigms for what you actually want to do with a problem like this in terms of how do you actually model it and what kind of properties you want in a solution. So one, generally speaking, one is to think about it in a stochastic optimization where we really think about it like minimizing or making sure that the constraints are satisfied in expectation, say. There's also robust optimization or distributionally robust optimization where you say, I wanted the constraints to be satisfied if the random variables are within some family of probability distributions and so on. There's also chance constraints. You want the constraints satisfied with some high probability, say, and within each of these, there's different challenges related to convexity, non-convexity, different levels of how many algorithms are out there to solve. Okay, but this is something that is widely studied, various different types in the literature now. What I'm going to talk about today, though, is a slightly different kind of formulation, which maybe is related to the previous one, but we're going to look at it in a way where the most important thing for us is that we want to assume that the constraints that I have are deterministic. So they could be general nonlinear constraints, but they are deterministic. But what I'm trying to optimize is an objective function that's defined as an expectation or maybe a large finite sum. So this would be like you have a stochastic optimization problem with deterministic constraints. There are, some ways of solving this problem that have been looked at in the literature. So one possibility is to, well, if familiar with stochastic optimization methods when there are no constraints, then you can say, well, I'll just throw these constraints in the objective with a penalty, and I'll apply my unconstrained algorithm to it, and then hopefully that I'm able to solve the constrained problem. And I would argue that some problems that people have been studying that are very popular now, where you have maybe an objective, a data fitting term plus some regularizer, a lot of times that regularizer is really just sort of a proxy for some constraints you might want to really impose explicitly. But the trouble is that adhering to those constraints as hard constraints is difficult, so we usually throw them up in a regularizer and then look at it as an unconstrained problem. But we're interested in thinking about things when you actually leave them as constraints and ask, how do we solve a problem like this, or what are potentially efficient methods for solving this? And we're going to hopefully make the algorithms efficient by actually handling the constraints as constraints and not doing something else. In that setting, we do need to establish what we want or expect from an algorithm, because there's sort of a big spectrum of what you can consider here. So on the one hand, you can imagine that you want to have an algorithm that works in what I would call the fully stochastic regime. Like, just like if you didn't have any constraints and you're applying a stochastic approximation, stochastic gradient method to, basically minimizing an expectation, you would want to be able to just say, let's think about your objective as a large finite sum. You want to be able to choose like one or just a small handful of terms in that sum, compute an approximate gradient with those, and have your stochastic type algorithm based on that. That would be what I would refer to as the fully stochastic regime. On the other hand, you could have algorithms that actually impose certain accuracy requirements on the gradients, so that depending on certain internal conditions in the algorithm, you might require yourself to have more accurate gradients. And then you can have different types of algorithms that maybe even behave almost like their deterministic counterparts. For us, though, we want to work in this sort of fully stochastic regime. And we want to also impose some different, expectations or desires of what kind of regime we want the algorithm to operate in. In particular, we don't want to consider algorithms that are what you would call feasible methods. So this would fall into the category of, methods where you're optimizing over a constraint set where it's easy to do projections, like optimization over simple convex sets or over manifolds where you can do projections. We don't necessarily want to look at the algorithm, those kinds of approaches, because if you have, for example, nonlinear equality constraints, doing these kinds of projections not only could be expensive, or they might not even be tractable, really. So we're sort of putting aside projection methods, Frank-Wolf methods. That's not the game that we're playing here. Related to that, we're not in the game of doing a two-phase methods where I get feasible first and then optimize. Like, we really want to do optimization at the same time that we're doing, of finding a feasible point. So feasibility and optimality at the same time, more like what the deterministic constraint optimization algorithms do. And because we're working in this fully stochastic regime, we have generally sort of minimal requirements what we want to prove. There could be more than what we do in the papers that we have so far, but we're going to be talking only about convergence and expectation. You could go further than that and still work in somewhat of a fully stochastic setting, but for us, we're looking at convergence and expectation, and you'll see how those results look as we go forward. Okay. So hopefully the sort of setting is clear and what we want and what we're hoping to achieve. Now I'm going to simplify things a little bit, and we're going to, at the end, I'll get back to the case of having inequality constraints. But for us at the moment here, we'll be thinking about having equality constraints only. And in fact, when you're talking about general nonlinear constrained optimization, the idea of having equality constraints only is usually a good starting point. You don't have to worry about, in terms of inequality constraints, identifying active constraints and having complementarity conditions. So this is actually an easier setting to start with. This is where we're going to begin. So it turns out that we need to actually step back and look at first the deterministic setting and design an adaptive method that will work in that setting, because it's only with that kind of approach that we're going to be able to move to the stochastic setting. So I'm going to go through both of those, and I'll give our overall results at the end. Okay. I'd like to give you actually a glimpse into how this sort of, in terms of the algorithm design, in terms of how the theory works. And to do that, I'm going to take a step back and talk about the stochastic gradient method, which is maybe something that many of you know, and you're perfectly familiar with all this stuff. And what I say here is going to be simple and easy, but at least I can then establish things that are going to be useful for us later on when I reference our constraint set. By the way, I always like to give a plug now. The stochastic gradient method, or stochastic approximation, goes back to Robbins and Monroe, and Monroe was a former Lehigh faculty member, so it's very hard to find a picture of him. This is a picture of a picture in our hallway in the department, actually. Okay, so stochastic gradient method. Just think about no constraints, just an objective function defined by an expectation or maybe a large finite sum. It's maybe not the best choice of notation, but this is what we did. Anytime you see a bar over a quantity, this is something that in its given iteration is stochastic. So the G bar here is a stochastic gradient, and the true gradient we just call GK. So the algorithm is pretty straightforward. We have some prescribed step size rules, and that the choice of that affects the convergence, as I'll say in a second, but you are just basically taking these negative gradient type steps with the stochastic gradients. We're going to assume that we have unbiased gradient estimates. You could extend that in different ways, but we're going to assume unbiased, and then we have some kind of bounded variance condition for these stochastic gradients. What is this sort of core idea in terms of why this algorithm works? Well, I don't call it SGD, I call it SG because it's not a descent method, although you do get eventual descent in expectation, and you've probably maybe seen this kind of analysis before for people who have worked in this stuff. You basically say, well, if I assume that I have a function, my objective has Lipschitz continuous gradients, then I can upper bound changes in the function by some quadratic involving that Lipschitz constant L. And then by plugging in what the algorithm is doing, taking this negative gradient step, you can say that the expected sort of change in the objective is bounded above by, and this is what I want to point out here, a term that is a term that's proportional to just alpha, and the true gradient squared, where the true gradient, as we know in the unconstrained setting, is like an optimality measure, the norm of the gradient there. So by taking these steps, we're sort of going to force this measure to 0, except for the fact that there's this noise term. And so the noise term is an alpha squared term that involves the stochastic error in the gradients there. We're able to drive convergence by making the alphas sufficiently small so that the error term doesn't dominate the descent term. So it's basically a particular choice there, either sufficiently small step size or by driving the alphas to 0, we can prove various things because of this sort of upper bound. So as is well known, I'll just mention in the non-convex setting, we're not assuming convexity here. If we have unbiased gradients and variance, bound on the variance, then we can say if I have a step size that's like 1 over the Lipschitz constant, then I can show that in expectation, my average gradient over all my iterations is sort of bounded. So I'm not getting too far in expectation from the region where I have small gradients. And if I actually drive the step sizes to 0, like 1 over k, then I can get a kind of limit for resolve in expectation for the true gradient. This is common standard stuff. So this is just sort of all being derived from that one sort of descent with noise kind of condition. Okay. And of course, if you look at the behavior of the algorithm, on the one hand, with a fixed step size on the left, here's just the contours of some objective, you bounce around in a neighborhood. On the right, you can get convergence, but it may be slow because you're driving the step sizes to 0. All right. Now, what you may be less familiar with is constrained optimization, but in the sense of what's the sort of standard ideas there. So again, I'll just give a brief history on SQP. Really, when you only have equality constraints, SQP sort of reduces to a Newton type method. But you can look at it, derive the algorithm in sort of 2 ways. On the one hand, you could say, okay, I have an equality constraint problem, and I write down the optimality conditions or the stationarity conditions. That's the sort of first order conditions on the left here. Or I could think about it as taking the original problem in a quadratic model of the objective, affine approximation of the constraints, and I have this QP subproblem there. Either case, if I solve this subproblem or I think about applying Newton's method to the optimality conditions, I end up having I can think about an algorithm where I'm computing my search directions by solving linear systems of this form. And this is a sort of classic symmetric indefinite systems that arise in like these saddle point problems, basically what you're doing here for solving this kind of problem. So we have that in approach. Now, when we think about this in terms of optimization, the key thing about SQP is that the philosophy is essentially that you're computing this step and that's what you trust. You've set up an approximation of your problem and that's what you trust as being a good step. And if anything, you will adjust your algorithm in a way that says that's a good step and I want to take it. And when I say adjust your algorithm, what I mean is that step could actually lead to different possibilities. You could have nice consistency. Basically, the objective and the constraints could be telling you to move in the same direction. Like kind of on the right here, this one I'm drawing is imagine this is the affine approximation of the constraints. This is a contour of a quadratic approximation of the objective. Minimizing the model of the objective over the model of the constraints, you'd move down here. And what this would basically be saying is, by moving to this point, I'm both moving towards feasibility, and by coming inside of this contour, I'm actually improving the objective at the same time. There could be other situations, though, like on the one on the left, there's a little bit of a disconnect between the objective and the constraints. I actually am going a little bit farther than I would want to for the objective because I'm trying to get towards the constraints. An even more extreme case would be if the affine approximation of the constraint said move this way, and the objective is saying move in the total opposite direction, you'd have this real opposing views of what the constraints and the objective want you to do. But SQP would push you towards the constraints because you have to satisfy those approximations as part of your subproblem. And if that means the objective might have to go up, that's fine. That we accept that. And the way that we balance this in terms of coming up with a full algorithm is that we introduce what we would call a merit function. But this merit function is going to have to adapt to what we see happening by the steps we compute. So a typical type of merit function that you might use would say, okay, I want to minimize my objective, but I'm going to put a multiplier on it. This is my merit parameter I'm going to call tau. And I'm going to add that to my constraint violation. And ideally, by minimizing this merit function, I'm going to find a solution of my constraint problem. If I minimize this, and it turns out that at a minimizer of that I find that the constraint violation is 0, the norm of C is 0, then I've solved my constraint problem. This relates to sort of exact penalization ideas and constrained optimization. okay? But that might only happen if tau is sufficiently small. So for an SQP algorithm to converge towards solving the constraint problem, I might need to decrease the weight I put in the objective in order to make sure I get feasibility, because you need that to solve the constraint problem. And so I want to potentially adapt the merit parameter. And what I'm describing here is not in the rest of this slide here is actually pretty classical stuff. SQP for constraint optimization, you basically, it's one way of updating the tau. You do it based on, you compute your search direction, and you want to do it in a way that you're actually going to get descent in this merit function. So the overall algorithm looks like this. Some of the details are not super important, but the idea is you compute your search direction from your linear system. You might change the tau, you might decrease it by using a rule of this form. The details don't matter, but there's some rule you'll have for potentially decreasing the tau. You've made sure that you're getting descent in your merit function, and you might do a line search from there. And this kind of algorithm is sort of state-of-the-art SQP type method for equality constraints only, and very good performance in practice, and all kinds of convergence theory with some additional bells and whistles and all kinds of extended settings. For the simplest setting, which I want to focus on here, you make assumptions like, okay, the functions and derivatives are bounded, the singular values of the Jacobian are bounded below. This is, related to the idea of LICQ, linear independence constraint qualification. Let's just assume that for simplicity, we have some second order sufficiency in terms of our choice of the H matrix there and our model of our objective. And from that, we can prove a lot of nice things. You can prove that your step sizes will be bounded below. You can prove that the merit parameter sequence will eventually remain constant, and that by driving the merit function, then minimizing that, we actually can show we get our stationarity conditions, basically being satisfied in the limit, so that you get feasible, and this dual stationarity measure eventually goes to 0 too. So that's the sort of background on SQP. We want to talk about the idea of using this, though, potentially in this case of having only stochastic gradients of the objective. And how do we do that? Well, our philosophy here, and there's different approaches that one could take. Our philosophy here is to say that line searches may be intractable. And you could talk about the setting of maybe stochastic line searches, and that's something that's one of the possible extensions of what we're discussing here. But I'm just saying, let's suppose that we can't do line searches. We don't want to do line searches. We want to have prescribed step size rules like we would have for stochastic gradient. Can we get convergence guarantees with that? And so to do that, the first thing we needed to do is actually go back to the deterministic setting and say, well, what would I do there if I'm not doing a line search? The algorithm I showed you before was doing a line search. What would I do instead of a line search in this setting? So we'll describe exactly what kind of approach we could use there. We call that an adaptive SQP method. I'll explain why. And that's the one that we'll take to the stochastic setting and hopefully get a convergence from that. So we'd like to have a prescribed sort of step size rule. But the challenge, though, is that we have, we're trying to solve a constraint problem that in some sense we translate to minimizing a merit function. But there's two things that are happening. The merit function is changing as we are optimizing because we're adaptively changing the tau. And what's also happens, at least for the merit function we're using, is that it's non-smooth. And so you can't just look at like a 1/L type step size that you get for a smooth function. You got to do something a little bit different. Long story short, what we do is a sort of similar thing you do in the case of a simple gradient descent method is you try to come up with an upper bound for your change in your merit function. This is not a smooth function of your step size. So, but all that really means is that you end up with a couple different cases. There's, different places, different situations and where the kink is in this sort of one-dimensional search you're looking for along your search direction. So whether the kink is before or after the minimizer, you end up with these different cases, but we can put it together in a nice formula with different conditions, and we can do a sort of sort of a fixed step size rule for our minimizing our merit function. And with that, we end up with an algorithm that looks like this. So this is, again, still the deterministic setting. We compute our search direction from solving this linear system. We update our merit parameter using the same idea as before to make sure that we have the right balance between objective and constraints. And now all of this stuff is really just about finding the minimizer along the array of our upper bound for our merit function. And if we do that, we can prove that we have convergence on par with the regular deterministic algorithm that has a line search. We wrote it here in a way that you're adaptively updating Lipschitz constant estimates, because you might want to do that instead. But if you assume that you know Lipschitz constants, then you can just use those. You don't have to do any of that adaptivity. So here's the next, suffice it to say, the next couple of slides is really just saying, if I do this in the deterministic setting, I get everything I have when I do a line search, at least in terms of convergence guarantees and so on. I'm not saying that this algorithm would be better than doing a line search. If you can actually compute function values, then I'm going to guess that the algorithm that does a line search would be more effective. But at least we can show that it will converge. So you can say that you have, again, a lower bound for your step sizes. If you have constraint qualification, then your merit parameter will eventually remain bounded. Everything works out in a nice way as before. But that algorithm now, especially if we assume that we know Lipschitz constants, we can actually go to the stochastic setting and say, can we basically take that framework, plug in instead of a true gradient, a stochastic gradient, and show that we get convergence guarantees? Because if it is, then we have an algorithm for the stochastic setting that is just like a state-of-the-art one for the deterministic setting, and might actually, it has convergence guarantees, but also work really well in practice. And we've actually seen that. Now, when it comes to the convergence guarantees, though, which is what I want to talk about next, there are some additional wrinkles that come up, and I'll try to explain those. So basically, in the nice case, everything will work great, but there's some caveats, and those caveats are really sort of important and challenging for the theory side of things. But at least we know the algorithm seems to work pretty well, and I'll try to explain all that. So we're going back now to the stochastic problem. So what I mean by that is our objective is like minimizing some expectation or some large finite sum, but that we have these nonlinear, non-convex constraint functions defining our constraints. We'd like to keep things like for stochastic gradient, where we only assume that the stochastic gradient estimates are unbiased and have some bounded variance assumption. Our linear systems then look like we have on the bottom of the page. And what's important to point out here is we have to think of, at a given iteration, if you condition on the fact that you've reached a certain iterate, some quantities in that iteration depend on the stochastic gradient that you're going to compute, and some don't. It's very important here in our setting that we know that the constraints are deterministic. So for example, conditioned on being at a certain iterate, this constraint value and the value of this constraint functions, that's deterministic if in the sense that it's conditioned on a certain iterate, those are determined values. Same thing with the constraint Jacobians. And if I assume the same thing about the H that I'm using, that it doesn't depend on the stochastic gradient, then the matrix here and the bottom term here are all independent of the stochastic gradient. But the stochastic gradient appears here. And of course, then the solution, both components of the solution are now stochastic. And that comes up in terms of our analysis, of course. We would like to be able to just take the same framework from before and just run it with the stochastic gradient in place of the true gradient, and hopefully things work out. And that's basically what I write here. What I introduced, though, here, before when I was talking about stochastic gradient, there was that alpha. And there alpha was this step size parameter that we could set to a fixed value to get a certain type of convergence guarantee. Otherwise, we send it to 0. Now what I'm going to introduce is this beta. And the beta is basically going to play that role before. My rules here are still about minimizing some upper bound for the merit function. So I still call those alpha, but the alphas are now influenced by the betas. The betas are going to be the thing that we can play with to get to different convergence guarantees. We would like this algorithm to work. Unfortunately, this doesn't quite give enough control on the step sizes to guarantee things. So we have to add one little extra part to it. This is just repeating what I was saying here about what the betas allow us to do. We can consider fixed betas for certain guarantees, diminishing for others. Unfortunately, it's not enough control in the step size. The problem is that because everything is sort of adaptive now, in the sense that we're not just using a fixed step size rule, we're trying to minimize this upper bound of this merit function, things could fall apart. The step size we get could be too small or too large. And so what we have to introduce is this idea of there's going to be a range we're going to impose. And if needed, we're going to project our step size into this range. And here, this range you can really see is, if you sort of ignore a little bit the beta part and the tau part that comes in from the merit parameter, what you really see here is something like a 1 over L type step size. We actually have L and gamma. L is the Lipschitz constant for the objective, the gradient of the objective. And gamma is a Lipschitz constant for the gradient of the constraints. So basically that it naturally pops in because that's influencing our merit function and everything. So basically, as a sort of backup, we need to project our step sizes onto this range because this is the range that actually work out in terms of our convergence guarantee. Fortunately, though, we can allow this value here, this theta, to be any positive parameter I want. So I don't really have, if I just set that as some huge number, the theory still works out. And then practically the algorithm is then not really affected by this projection interval so much. Okay. We're in the center of the technical stuff. So, I mean, hopefully you can follow the main idea so far. If you remember back to what made the stochastic gradient algorithm work, it was the fact that you could bound the change in the objective and expectation by a term that was essentially deterministic, that was related to an optimality measure that was like an alpha term at that then. And then there was the noise term that was like the alpha squared term that if you played with the step sizes, you can get things to work. The same kind of thing happens here, though we end up with this extra term. The first thing here, even though I write it as alpha, this is really like an order beta term. And this delta Q, as I'm going to say in a second, is really something that plays a role of an optimality measure. So this is like the descent term that we get from the way the algorithm is structured. This is going to be basically clearly a noise term, okay? That's an order beta squared term. Again, look at it as like the D is the step that I would have gotten if I used the true gradient. The D bar is the step that I get because I'm using a stochastic gradient. On the whole, this is like a deterministic quantity. This is like a noise term. And there's one more term that pops up because of the fact that we're not just using a fixed rule for the alpha. We have this range that we're getting from minimizing the model of the merit function. Long story short, though, we can show that that's going to be like another noise term, and we can get things just like stochastic gradient. So if I assume things like I said before, unbiased gradient estimates, just a variance condition on the noise, then I can prove that in expectation, the stochastic steps are the true steps in expectation. The multipliers are the same as well. I can show in expectation, the difference between the stochastic step and the true step that I would have gotten if I had the true gradient is bounded like a noise term. And then these are some a little bit tedious to get to, but they show that certain inner products are bounded between stochastic quantities and their corresponding true quantities. And that becomes critical in the analysis. Here's the main result that we can prove. The one caveat on this is that we have to make an assumption. And the assumption that we have to make is that eventually the merit parameter sequence remains fixed. Now, I will say in a second why that might be still a reasonable assumption, even though we can't prove it always happens. I'll say more about that in a second. But under that assumption, if the merit parameter eventually remains fixed, then that extra term in the noise is just like a beta squared term, and I can prove things just like at a high level. If you blur your eyes a little bit, this looks just like you saw for stochastic gradient, where if I have my step size parameter now beta, that's sort of a constant, sufficiently small, then I can show that the average of these delta Qs, which I'll say more in a second, is bounded. Otherwise, I can get this converging to 0 if I send the betas to 0 at an appropriate rate. These delta Qs, by the way, are really playing a proxy for a certain optimality measure, basically between the constraint violation and the error in the sort of dual optimality condition there. So as a corollary to that previous theorem, you can write in place of the delta q's, you can put these things. And basically, it's like saying if I have a fixed step size sufficiently small, I get to a place where the optimality values are going to be small in expectation, and otherwise I can get a kind of lim-inf result for the optimality conditions to go to optimality errors to go to 0. Okay. Now, that's the main thing that we can prove in the nice case. If we have to talk about those caveats though. So what about this whole idea of assuming that the merit parameter sequence is good? At a high level, what I'll say is that, well, first of all, if you actually had bounded noise, then you would never have to worry about, for example, the taus going to 0. It wouldn't happen if you had bounded noise. Also, if you have things like the the error, if you have like sort of stochastic gradients that satisfy certain like sub-Gaussian distributions, so the errors is sort of fast decay in the tails, then they would stay. Then the tau would not go to 0 with high probability. So you can even prove things like that. So if you think about running the algorithm for some number of iterations, its probability you can say is relatively small that the tau gets very tiny in those iterations. So that's at least some comfort there. And I'm obviously not including the main details there, but that's at a high level. The other thing that can actually happen is that the tau could remain too large. And what happens when the merit parameter stays too large is that by minimizing the merit function, you're not actually pushing down to 0 the optimality error for the constraint problem. But that one is actually even more sort of easy to write off as not a big deal, because really the only way for that tau to remain too large is if you really have sort of, think about the way your stochastic gradients are, and a distribution around the true gradient. It's only going to happen if they're really like one-sided. Like if the stochastic gradient, the error is always sort of one-sided in the stochastic gradients, then this might be a problem. But in general, if it's sort of symmetric around your in some sense, around your true gradients, then this is not going to be a problem either. Okay, so I'm trying to write off, like kick under the rug a little bit some of this bad stuff, but we've done some work to try to argue that these things are not really a problem for practical purposes. So, okay, let me tell you a little bit about some experiments and then some about some extensions that we've done. So these are relatively simple experiments that we did. The cute problems is this big standard test set for constrained optimization. Many small problems. These are not big problems, but there's a lot of them. So that at least is good. And the only comparison that we did was comparing our algorithm, where for each problem we run it, I think it's like 5 or 10 times we ran it with an iteration limit and see the result that we get. And we also compared it to a stochastic subgradient method, where for that one, you just formulate the constraint problem as just minimizing a penalty function. And we tuned it over different values of the merit parameter, or the penalty parameter, I should call it probably. And we even let that algorithm do 10 times as many iterations as ours does. And so by this process, we're basically trying to give as much allowance for the stochastic subgradient method to do well and find a good solution compared to our algorithm. These plots in the bottom try to show that with these runs, our algorithm generally performs better. And what we mean by that is we run all the algorithms with these settings that I said, and we try to take from each one what is the sort of best iterate. And what we mean by that is if we've gotten iterates that are relatively feasible, and hence the feasibility error is below 10 to the minus 6, then we try to choose the one that gives the best stationarity error, a KKT kind of error. Or if it didn't get feasible, then we just sort of taking the most feasible iterate and look at it that way. But so what we plot here is a box plots for different noise levels. So these cute problems are not stochastic alone. They're really deterministic. So we just add noise to the gradients. So for low noise levels versus high noise levels, long story short, our algorithm is often getting feasible, so finding feasible solutions. I think the main attributed factor to that is that we don't mess with the constraints. We leave them as constraints, and we try to solve the problem that way. So generally speaking, we're getting more feasible, and we're also getting better in terms of KKT error, stationarity error from there. Now, you might look at this and say, well, your algorithm does a lot of more work per iteration. You have to solve this linear system, stochastic subgradient, you don't have to do that. And that's true. But that's also why we have some of the extensions that I'm going to talk about here. Okay, so this is at least in our minds confirming the fact that this is a good algorithmic approach that we would try to push further and go far. So just very briefly in terms of some extensions here, we have various things that we've done. So one thing that we've done already, and at least the paper is submitted, is to try to loosen some of the assumptions that we made. So one of the things that we assumed is that we have constraint Jacobians that are always, the singular values are always bounded away from zero. You want to relax that assumption. You may have a singularity of your constraint Jacobians. This is a classical assumption you want to remove in the constrained optimization literature. So for us, we remove that. We have a slightly different algorithm now that looks at a step decomposition method, which is again borrowing from the deterministic literature on doing that. There's some additional complications in terms of the analysis, but long story short, we got an algorithm that we were happy with in terms of what we can prove, and also experimentally looks very similar when we compare to the stochastic subgradient method. In these experiments here, we made sure that all of the problems actually have rank deficiency. So we're really pushing it in terms of trying to solve challenging problems, the rank deficiency in the constraint Jacobians. So that's a work that's been done and is under review. Another thing that we've also done is under review is looking at matrix-free versions of these. So imagine that you don't want to solve these potentially very large-scale linear systems to compute your search directions. You'd like to maybe apply an iterative method and use inexact solutions of those linear systems. This is related to some work that I did back during my PhD, actually, bringing it back again. But here we actually have inexactness and stochasticity from the gradients. So relatively complicated in terms of the analysis, but the algorithm is relatively straightforward if you're familiar with these kinds of things. So again, though, what we end up with is an approach that is some improvements from inexactness. Now, here the comparison that we're doing on this slide is between an algorithm that is the same framework that I mentioned before, where we solve the subproblems exactly versus inexactly. So the exact one is the blue, the inexact one is the red. And trying to show here that even though in some cases the exact algorithm can do well, because of the expensive subproblem solutions, if you introduce a budget, there's actually some cases it's not even able to get feasible. And so where the inexact algorithm is able to move more quickly within the budget and get to good feasibility and also better in general in terms of optimality. I could say more, but I'll just leave it at that. So we've been working on reducing the cost of the subproblems. Another work which is not submitted yet, but we're wrapping up the paper soon, which does end up being quite complicated, but I'm pretty excited about the result that we have, is to look at worst case complexity. And this is something that people are usually interested in for these algorithms. What about the worst case performance? The main challenge for us is, yeah, we want to solve a constraint problem, but we know that's really sort of related to minimizing a merit function. But the problem for us is that merit function is changing. And so imagine doing your complexity analysis where you're minimizing some objective function, but now your function is changing adaptively during the optimization. And so that sort of puts all kinds of other analysis under out the window. We've got to do something at least a little bit different to account for the fact that there's these changes in the function. Long story short, what we believe we've come up with, we're still wrapping up the final details, but we believe what we've come up with is that, and this is very consistent with what's in the literature about complexity bounds for stochastic gradient type things for non-convex objectives. You say, okay, I'm going to have a prescribed number of iterations. I'm going to have a certain step size rule. And then in the end, I'm going to prove something about a random iterate that I choose with a certain distribution over all the iterates that I've computed. And you'd like to be able to show something about the expected error from optimality error or something that you have from that iterate that you computed. Now for us, the additional wrinkle that comes in is that we have a fixed number of iterations that we're going to perform. And we're also going to say, let's suppose that we decrease the merit parameter some maximum number of times. That's what the S max is. So K max is the iteration limit. S max is the number of times we decrease the merit parameter over those iterations. And that can be random in different runs, it might change. What we've been able to show is that in expectation, the optimality error is bounded above by a sum of terms. The first term is basically reminiscent of what you see for the unconstrained setting. It's basically the initial error divided by, this is sort of written in the form of a convergence rate, but you could convert this into, if you just had this term here, it would be like an epsilon to the -4 term that is typical for what you see for stochastic gradient, subgradient in terms of their complexity. The problem though is that we have this extra term, and this pops up because of the potential change in the merit parameter over the iteration sequence and the number of times we might decrease the merit parameter. On the surface, this is like sort of the first result that you would show. Well, we can also show that on top of this is that with certain assumptions about the stochastic gradient, just like I was saying before, like maybe sub-Gaussian or something like this, you can actually prove with high probability at least that S max is small, considerably smaller than K max. And so this term here becomes something that's really a sort of log factors of K max. So you eventually get complexity that's comparable in some sense, at least with high probability with the unconstrained set. The question people have often asked me that have seen this so far, they say, this is weird that you have a complexity result where you say the expected value is bounded by something, but only with high probability. But it's the only reason that you have with high probability is because the uncertainty in this adaptive merit parameter. If we knew the merit parameter value in advance, this would not be with high probability. This would be a sure result in expectation with this convergence rate that you can turn into, as I said, a sort of epsilon to the -4 type bound. All right. The most recent work is in inequality constraints. And in some sense, I hesitate to say too much about this because it's ongoing work, and just to make sure that we don't give away too much of our secrets here and what we're trying to do anyway. We're working on the inequality setting. By the way, there is some current work that people have done in this space on inequality constraints. I mentioned earlier the setting where you are not in the fully stochastic regime, but you're more maybe adaptive. You're adaptively updating your stochastic gradient estimates to satisfy certain conditions. I referenced a paper there by Mihai Anitescu and his team. They've been working with inequality constraints already, and I saw a paper in arXiv already about that. But for us, we're working in this sort of fully stochastic regime, and we still are under development of our methods there, but we're basically trying to take our ideas from the equality constraint case and apply them here. The challenge is that we lose a little bit of, before it was nice because things remained unbiased. The solution that we compute in expectation is the true step that we would have gotten if we had the true gradient, but we lose that when we have inequality constraints. There's a whole host of open questions here about, especially if you want to talk about, okay, what about estimating active constraints at the solution, or getting good multiplier estimates, even in the equality constraint case. There's a lot of open questions there you can go on, and these are things that my group is planning to work on. But so this is like sort of just reference that this is ongoing work, basically. Okay. So with that, I'll try to wrap up now. So in terms of a conclusion, we've been talking about stochastic optimization problems with deterministic constraints. By the way, I do hope that the algorithms that we can come up with could also possibly be used in other settings, like when you actually have maybe stochasticity in terms of your constraint, like your probabilistic constraints and so on. I mean, there are some algorithmic methodologies in that space, but the things that we do, I hope, could also be useful there as well. But for whatever we're doing, we're talking about deterministic constraints, is stochastic objective. I focused on the equality constraint case, although the other extensions are ongoing. Our one paper has already appeared. If you want to take a look, the two others are under review, and then we have the paper on complexity bound that's sort of going to be coming out soon, we hope. talked about the convergence and numerical results. A lot of it is preliminary because I think this is sort of a new, there's not many articles in the literature on this in this direction. So there's a lot of things for people to do if you're interested, and I'll be happy to talk more about other possible extensions too if you want. But before I do close, and we're getting at the end of time here, before I do close, I just want to give a plug. I was mentioning this for those of you who were around earlier, that ICCOpt, if that's the conference you've been to before, is this International Conference on Continuous Optimization. The last few were in, as we were saying, Berlin, Tokyo, and Lisbon. Next year is going to be at Lehigh, sort of late, well, I guess sort of middle of the summer there, in the middle, at sort of end of July. It should be, we're planning it to be an in-person conference. We hope that the world allows that to happen. And if you're interested, hope to see you there. It shouldn't be too bad of a trip from Montreal to get down here. So just wanted to give that plug before I finish. And I'll leave it at that. And thanks very much. All right. I don't know, I don't know if I looked at the chat. Do you want me to go from there, or?
I think I answered that one question in the chat, okay. But maybe maybe you want to add to that. But I think it got clearer after a few more slides.
Okay.
Yeah, but so thanks a lot for this really very clear talk and super interesting stuff. So the floor is open for questions, but usually people are very shy. So I'm just gonna start. I'm just gonna try to put some energy in this system. Maybe something will happen. So maybe I missed this, but did you talk about how you choose the matrices HK?
Yeah, that's a good question, and really we left it pretty open in the analysis. So the simplest thing would just be to have it be the identity, and that would be like a first order method, and everything then is clean in terms of the analysis. There's no dependence on H on the stochastic gradients. There's no worry about it being ill-conditioned or singular. So that would be the simple choice. On top of that, you could do various ideas, like people have tried to do quasi-Newton or subsampled Hessian methods. It's just, you just run into the same challenges that you run into in terms of the unconstrained setting, where you got to make sure that they are, first of all, not that they have some independence from the stochastic gradients, because otherwise that correlation could be a problem. You also worry about ill conditioning and various things. In our experiments, we were just doing it with the identity. Although I would hope anyway, because I'm a big fan of second order or quasi-Newton methods, that in reality people would try those things because they could work well too. But yeah, the theory makes it, we tried to make it very generic, but at the same time simple. Like, so we do assume that you have that H is positive definite in the null space of the Jacobians. That's the standard stuff for constrained optimization. We didn't want to get into the other things for that, and so that's all we've done so far for that.
Okay. Well, I have a couple more questions. So please, everybody, feel free to unmute yourselves or write questions in the chat, because I think we have a few minutes for sure, because we're really quite on time.
Can I ask a quick question?
Yes, of course. Go ahead.
Hi, this is Sam Davando. I'm from ISC OSU. In your optimality measure, you had like a squared norm, just quickly to check. You had a squared norm on the gradient of the Lagrangian, and also you didn't have a square on the constant violation, right?
Right. So I think you're pointing at, well, it pops up in a couple of places. It pops up here in this complexity bound,
yeah,
and,
exactly.
And then it also pops up in our first result here. Well, I didn't write it that way here, but you could get it there as well. I mean, let me go back. Let me go to the complexity one though. Okay, because this is really where you see it, why the choice of the norm squared versus the norm pops up. It basically comes out of the analysis that turns out to be kind of a natural way of measuring optimality. I'm trying to think of the best way to describe it. I mean, in a sense, if you only care about those things vanishing, doesn't matter what norms you use, right? But when you look at the way that what drives our algorithm is reductions in the merit function once the parameter gets small enough. And the way that we have our merit function defined and what you get from our step is basically the natural thing is to have just the norm for the constraint violation and the norm squared for the basically tangential stuff. Basically what happens in the analysis is that sort of towards the constraints, there's really, you think about each step as having two components, towards the constraints and in the null space towards optimality. And because of the way our merit function is structured and the model that we use for it, it's natural that there's sort of different norm choices in the two dimensions, or two components. So it really just pops up almost automatically. And that's the best I can describe without pointing to the other, but it just pops up.
Thank you so much. This complexity results in your second work, right? Is it on archive?
This one's not on archive yet. We're finishing up the last parts of it. I mean, it's pretty complicated with the whole the function changing as we go. So we're trying to make sure that things are hopefully as clean as we can get them at best of our abilities. And so that will hopefully get out in archive in the next month or two. That's our hope. Yeah.
Thank you so much.
Sure.
Further questions? I have one other question. So the usual little illnesses that SQP has are like subproblem infeasibility, but that doesn't really change for you because your constraints are deterministic. So is that still the same problem, or?
Yeah, it's still the same problem. Now, in the equality constraint case, things are actually a little bit easier. So that pops up in this when I mentioned no LICQ. So if you actually have, linearly independent constraint gradients, then the subproblems are always feasible. That's fine. But when you relax that, you don't. But this is where the step decomposition method comes in. You basically, instead of solving this subproblem exactly, you basically compute a normal step towards the constraints, and then in the null space where you might not actually get to perfectly linear feasibility. So that's the standard thing to do in the deterministic setting when you have that issue. Now, what's even more relevant or more important for your question, it's much more up in the air about what to do, is when you have inequality constraints, because there you might just have inequality constraints. You say you have to be here. If you introduce things like a trust region or something in your algorithm, it just might have total incompatibility in your subproblem. And that's one of the open questions that we think we have an answer to for ours, but you're right. I mean, it's the same issue. You have to be careful in terms of what you demand from the subproblem solution, or how you actually formulate your subproblems based on that.
And when you say no LICQ, do you assume like something weaker, or you just throw everything out the window and you can like MFCQ would be the next?
Yeah, right. I mean, we throw it out here, but the reason that we throw it out and it's okay is because we, at least for the papers that we've had so far, we haven't really talked about guaranteeing primal dual stationarity. The measures, and this is maybe something I also sort of swept under the rug. When we say an expectation, these things are going to zero, this Y is not actually something that we're computing in the algorithm. This is the Y that we would, this is the multipliers that we would get if we actually had the true gradient and we solve the system with the true gradient. We can prove that this happens even without computing those Ys, but we don't actually have them. Now, in terms of like, what constraint qualification you go to if you throw that out, well, it all depends. I mean, if you didn't care about primal dual stationarity, then you can really just throw them all out because you're just working in the primal space. But if you care about, and that's another thing that I would like to investigate for this kind of setting, is how do you actually practically try to come up like a practical termination conditions and practical stationarity conditions when the multipliers are based on systems that have stochastic gradients. Especially in the inequality constraint setting, that might be important because for certain algorithms for inequality constraints, you actually want to try to identify activities of constraints. And for there, you want multipliers and all that stuff. So, but it's an open question there, I think, in terms of how you do that.
Okay, cool. So maybe let's wrap up the question period and thank Professor Curtis again.
Okay. Thank you.